Hello, everybody. My name is Juuso Luhtola, and I'm a doctoral researcher at Aalto University. Today, I will talk about the topic of network centrality metrics based on unrestricted paths, walks, and cycles compared to standard centrality metrics. In this presentation, we will first look at the motivation for our study, and then we will introduce the influence spreading model, and we will show an example of how the influence spreading model works. And then we will introduce the new centrality metrics defined by the influence spreading model. And then we will compare these centrality metrics to standard centrality metrics, and we will do some detailed analysis and also some larger scale analysis or comparisons. And finally, we will discuss our results and draw some conclusions. So the motivation for our study is that many network centrality metrics depend on shortest paths between two nodes, or they are based on using the local environment of the node. So this means that other paths and walks that could significantly influence various centrality properties and flow characteristics in the network are overlooked. The influence spreading model proposes new centrality metrics which address all possible walks that are shorter than a maximum walk length. And this maximum walk length is a model parameter. And in this study, we compare these new metrics to degree closeness and between the centrality. Degree centrality is simply the number of nodes, number of neighbors a node has divided by the number of nodes n-1. Standard closest centrality is the reciprocal of the average length of the shortest paths between node and all of other nodes in the network, and standard between centrality measures how frequently a node lies on the shortest path between two nodes. We will very briefly look at the logic of the influence spreading model. Influence spreading model assigns probabilities for all edges in a network, and edges can either be directed or undirected. And we use the term walk, which is a sequence of nodes and connecting edges where the nodes and edges can be repeated. So we can have cycles, we can have backtracking in our walks. And in our influence spreading model, we explore all possible walks from a source node to a target node, with the only limitations being that we have a maximum allowed length, which is Lmax, and then that we terminate the walk upon arrival to the target node, regardless of how long the walk has been or how short the walk has been. And based on edge probabilities, we can calculate the probability of a walk. And then when we have different walk probabilities, or we have different walks and probabilities for them, we can combine these probabilities based on their common prefix walk, which is explained in more detail in the article. Here I will not go into the details, but their probability can be combined, which is consistent with the rules of probability. And here we have an example. In the top right-hand corner, we have a small four-node network which has undirected edges, and it has 0.5 probability as the edge probability for all edges. And in this network, if we have node 1 as the source and node 4 as the target, we have in total 10 different walks from node 1 to node 4 with walk length that is equal or less than 5. But if we go from node 4 to node 1, we have only 6 walks with walk length that is equal to or less than 5. The difference comes from the fact that first arrival to target node terminates a walk. So even though everything else is equal in this network, edges are undirected and edge probabilities are the same. The network structure causes this difference in the possibilities of how many walks there are, and then it also causes a different influencing probability when we combine these path probabilities. So when we calculate influencing probabilities, we eventually can get an influence spreading matrix where all the entries are influencing probabilities from node S to node T. And this influence spreading matrix and the entries are then used to define a new centrality metrics. First of them is out centrality, which measures how much a node influences other nodes on average, and in centrality, which measures how much a node is being influenced by other nodes on average. The influence spreading model also defines its own betweenness centrality, and at the heart of this calculation is how the sum of the elements of the influence spreading matrix changes when a node is removed from the network. And when we remove the node from the network, we also remove all of its incident edges. And then the influence spreading betweenness is calculated as this percentage essentially of how much these sums change when a node is removed from the network. The more there is change, the more important the node is in the sense of influence spreading model betweenness. Here we have an example of how the influence spreading model works. We have the famous Kragh-Kite network, which is famous because here the node 4 has the highest standard degree. Node 6 and 7 have the highest closeness centrality values, and node 8 has the highest standard betweenness value. And here we have compared how the influence spreading model betweenness compares to standard betweenness. We first see that the values of the influence spreading model betweenness, they change as the edge probability increases. Initially, the values in the network, the nodes who are most connected in the network, they have the highest betweenness values, but as edge probability increases, we see that actually nodes 8, 9 start to have the highest betweenness value, and the reason for this is that when those nodes are removed from the network actually breaks down into two different components. That is why they get so high influence spreading model betweenness values, especially for larger edge probabilities. And then we also here have compared the rankings to standard betweenness centrality, and we see that for higher edge probabilities, the rankings given by influence spreading model betweenness, they are very similar to standard betweenness rankings. Here we have compared out and in centrality to degree and closeness centrality. We first see that out centrality values have larger dispersion than in centrality values. We also see that out centrality rankings are similar to closest centrality and degree centrality rankings. And we see also that in centrality and out centrality have the same rankings for low edge probabilities. However, when edge probability starts to become higher, actually in centrality value rankings completely reverse. The last one becomes the first one, and so forth. And this is an important phenomenon to keep in mind. We then also performed experiments where we used network models, Eros-Renew model and Watch-Strogat's small world model and Parabasi-Albert preferential attachment model to create 3 different random network datasets which have 1,000 nodes and approximately 5,000 edges. And all of these networks have slightly different properties, or sometimes very greatly different properties. And therefore, these networks provide varied yet controlled conditions for our experiments. And as before, we have used the same edge probability for all. We have used the same probability for all edges. However, we increase the probability between experiments. And in all experiments, we use the maximum allowed walk length as 20. Lmax is 20. Here in this scatter plot, we have compared influence spreading model betweenness to standard betweenness. We see that there is positive correlation between these 2 centrality measures, and it is seen for every one of these random networks. And here we have the probability, edge probability is on top of each figure, 0.1, 0.3, 0.5, 0.7, and 0.9. And as the edge probability increases, the correlation starts to become weaker. Here we have compared out centrality to degree centrality. We see that for the Erdos-Renew and Watch-Strogat's networks, they have Poissonian degree distribution, which creates this really nice, almost linear correlation or relationship between out centrality and degree centrality. For Parabasi-Albert network, there is a nonlinear but positive relationship. And this nonlinearity is caused by the Parabasi-Albert having scale-free degree distribution, which causes very high degree nodes to appear in the network. And this causes this curve to appear in the figure for 0.1 probability. Here we have compared out centrality to standard closest centrality. Again, we see a positive relationship which starts to become weaker as the edge probability is increased. And we can also say that for low edge probabilities, closest centrality is a good predictor of out centrality in this experiment setting. Here in our final figure, we see in centrality compared to out centrality. We see that for the Erdos-Renew and Watch-Strogat's networks, there is quite strong positive correlation initially, which reverses into quite strong negative correlation. For the Parabasi-Albert network, there is actually the reversal is already happening for edge probability 0.1, but we are seeing the same phenomenon we saw with the rankings for the smaller Kragh-Kite network, but here we are seeing it in a different form, that there is first a positive relationship between in centrality and out centrality, and then it reverses into a negative correlation. And we have seen here that influence spreading model betweenness, it can detect the importance of alternative routes while maintaining similarity to standard betweenness centrality. But the downside is that there is great computational cost to calculate influence spreading model betweenness. And out centrality can detect central nodes as more influential nodes than peripheral nodes. And for higher edge probabilities, in centrality can detect peripheral nodes as the most influenced nodes. And the impact of the walk length, maximum allowed walk length, is that if it is longer than 20, then this reversing behavior in centrality happens earlier. If it's shorter than 20, then the reversing behavior happens later. And here are the most important references for this presentation. Now, I thank you for listening.